Hey guys, in this video we're going to be doing one of our last few topics here in AP Calculus, and this one is on finding the volume of what's called a solid of revolution. So I had another Edpuzzle assigned to you where you're supposed to find the volumes of solid using what was called known cross sections, which basically you create this three-dimensional figure and you chop it into whether it be triangles or semicircles or squares or something like that. Chop it into an infinite amount of those, add up all those areas, and that gives you a volume. It's kind of an abstract concept, so hopefully you at least got a little bit of idea what's happening here. I know it's challenging in this format, especially to fully grasp it. So in this video, we're going to still be doing the same thing. We're going to be finding the volume of a solid of revolution. This is just a little bit more common method. Both are on the AP test, but this is just more widely used, I guess you could say. And that is called the disk method. So in this video, rather than chopping this solid into either like triangles or squares or something like that, we're basically going to chop it into disks. So this is called the disk method. The concept of this is actually pretty simple. The disk method says that basically if we have some area, right, we got an area under a curve, and we integrate that, right? So we have this concept volume equals integral from a to b of some area of x dx that equals the volume, right? So we integrate this area and we get a volume. Volume is the integral of area. Very important concept here. Volume is the integral of the area. All right. And again, in these other videos, we saw we could chop it into different things. In this one, we are going to chop it into disks. Okay. So disks, you could think of like, like a old school CD-ROM, I guess, right? But without the hole in it, this is going to be a solid disk. So I'm going to try to draw a little bit of this idea here. Basically, we got the area of this, and we rotate this around. So we got what's called an axis of revolution, and our axis of revolution here is the x-axis. So the x-axis sort of forms like an invisible dotted line, and that's what we're going to rotate it around. So when we do so, we get a three-dimensional figure. This area just rotates all the way around the axis, and we get this three-dimensional figure here. So this becomes shaded, and this is actually a three-dimensional object that if you were to look at it, if I were to turn it a little bit, I'd sort of get this idea of like a circle there, and then it sort of goes like this and like this. And with this, I'm just going to chop this thing into an infinite amount of disks. So if I were to like pull out any one of these cross sections, if I were to just reach in here and grab one of those out, it would just be a circle. Each one of those little cross sections would be a circle with a radius of what we'll just call r. So basically we're finding the area of all of these, and we're summing them all up, because if you remember, a integral is just the sum of, right? So it means an infinite sum of areas. So infinite sum of these area of these disks, add them all up, and that gives us our volume. All right. The actual computation of this is pretty straightforward, and you may use a calculator, which I would advise. Just makes things a little bit easier. You can do these without a calculator, but we'll do a calculator just to make it a little easier on us. So when we're finding the area of a disk, right, this is the disk method. Well, the area formula for that is very straightforward, because the area of any disk, any circle, right, is just pi r squared. So our volume for the disk method is then just the integral from a to b of pi r squared dx, because area is just pi r squared, right? The radius is the only thing we really have to figure out, because that's the only thing we don't know. Pi is just obviously a constant. The radius is basically just going to be whatever the area under the curve is. It's just always going to be basically the gap from whatever our axis is to this curve. That represents our radius. In this particular one, this is r. So that just is going to be the area under the curve for this particular problem. There are some we're going to have to do a little bit different. But since this is revolved around the x-axis here, the radius of each of these disks, so you got all these infinite disks, the radius changes, right? Radius is changing because it's a function. The radius is a function. It's not a constant amount. The radius is defined by the function f of x equals x cubed. So to find this volume, it's just going to be the integral from our starting to our ending point. And this one, it says x equals 0 to x equals 2. So from here up to here, that's where we're going to integrate from 0 to 2. And remember, those are x values because our function is x values. And our function there is x cubed. I'm going to go ahead and write the pi there, pi. And then our radius is just the function, x cubed. So it's going to be x cubed squared dx. Okay, so our radius is just the distance from the x-axis up to the function that represents our radius. So it's just the function x cubed. And we're just going to go ahead and type this into the calculator. Again, you could obviously do this pretty easily without a calculator, but it says we can use a calculator, and on the AP test, if you can use it, then use it because it'll save you time. And all I'm going to do is just going to type this into my y1. So you just type into your y1. You're just going to type, I'm just going to type it exactly as it's written. You could obviously just go ahead and multiply those powers and make x to the 6th. But if it was more complicated, it's a good idea to just type it in as written, so then you don't have to worry about making an algebraic error. All right, so x cubed squared. So I've gotten written in. I'm just going to go ahead and graph it. Just going to just type in this into y1, and then graph. All right. And now, after you've done that, remember how we can do an integral in here is we do second calc, and then we're going to do the integral of f of x dx. Make sure you can do this on the AP test. You don't want to be stuck doing all these by hand, especially with big numbers. Ask you for your lower limit, so your lower is going to be 0, enter. Upper is 2, enter. And there we go. We get a volume of, it says round to the nearest thousandth, so 57.446. Tens, hundred thousands, yeah, 57.446. So that's all there is to it. 57.446. Boom. All right. I think this graphic they show you is kind of neat too. If you slide this, you can see how the volume kind of accumulates, and you can kind of see those disks as they grow. It's kind of neat. And your three-dimensional object there as well. All right, let's look at another one. Okay, this one looks like it might be just a bit more challenging because it's not revolved around the x-axis. It's actually revolved around a y value. So here's where it gets a bit challenging. All right, so we've still got the same deal here. This is our area, right? And this is around the line y equals -2. Okay. So when we revolve this one, still the same deal. We're going to revolve it around this. And so we get this idea of another, going to mirror that. And so we get this solid that looks like this. Okay. So our volume is going to be still just the area, right? We're going from, talking about x values. So we're going from x equals 0 to x equals 2 still. We got our pi, and then we need to talk about our radius. So unfortunately, this one, the radius isn't just going to be the function, because the function, if I were to just look at, erase part of this. Okay, if I were to just take the function value as my radius, well, that wouldn't quite work, because the area under the curve it would give me this, because it just tell me the distance between the x-axis and 0, and it would give me this. Those would be my two areas if I just took the function value. That's not what I want. So what I actually want is this gap from here to here, right? So how do I get that? That's a good question. Well, it's going to be, traditionally when we think of the area under the curve, it's actually whatever the function is. If I were to just look at this part, the area under this would actually be the function minus 0, essentially. So whatever that function value is minus the 0 value down here. That tells us kind of the space between it. So the only thing that changes is if instead I want to extend this down to here, I'm not going to stop at 0. I'm going to stop at -2. So my function is going to be my f of x minus 2. And actually, sorry, minus -2, because it's actually y equals -2, right? So I want to go all the way down to -2. Instead of f of x minus 0, again, that would tell you the distance between there. That'd be f of x minus 0. I want to go all the way down here, so I want to go f of x minus -2, right? So then when I plug this in for my radius, it's going to be x squared minus 1 minus 2 squared. Okay, that whole thing is going to be squared, dx. So hopefully that kind of makes sense. I'll try to do another one that's similar to that. But again, I'm just going to type this in exactly as it's written. That way I don't have to worry about if I square something wrong, because you would actually need to combine those and then you would need to FOIL it out. So easiest thing to do is just type it in as is. In your y1, I'm just going to type in pi, parenthesis, x squared minus 1, close parenthesis, minus 2, close parenthesis, and square the whole thing. The most common mistake in these is to forget to square the radius. It is pi r squared, so we got to square that radius. We're then going to graph it. All right. Second calc, and then go down to number 7, my integral. My lower limit is 0, my upper limit is 2, and I get a volume of 26.389. So this really isn't a hard problem to compute. It's just making sure you're getting the radius correct, which isn't as easy as it sounds. I know if we were in a traditional class, we would spend about a week doing these. It's hard for me to explain it in the course of a video or two, and you fully get a good grasp of it, but let's do the best that we can. My hope is with all these topics that you at least get a basic foundation. It'll give you a good chance on the AP test. If you don't pass the AP test, you know, that is what it is. The hope is that everyone can pass, but if you don't, you'll at least have a good foundation of calculus going into college. Let's go ahead and type that in. And oops, let's see what I did here. Did I not round it? Oh, sorry, I forgot to put in my negative in my y1 there. All right, should be minus -2. Let me try that. Retry that calculation. Oopsies. All right. You do have 2 chances, so plus. All right. Another common mistake, forgetting to, I guess, put in the negative value. All right, so you can see my integral there was the same. And I actually wrote it out right. I just didn't type it in my calculator correctly because I was talking while I was doing it. Let me try that again. Second calc. Integrate from 0 to 2. And that time I did get 43.1145. So there you go, 43.145. Sorry about that, guys. All right, let's do one more. At least one more. Okay, this is a good one because this is kind of the opposite. So whereas before we saw the axis of revolution was always below it, this one, our axis of revolution here, it says is the line y equals 1. And we're going to do the same deal. We're going to be rotating it around here. Okay, so here's my invisible axis. And then so it kind of goes up like this. And this gets shaded. So again, we're gonna like cutting out of these. It's like these discs here. An infinite amount of discs. All right, so my setup still going to be always the same. Integral from Now let's see what it tells us the x values. It's going to be 0, obviously, is my x starting here, up to 1, it looks like. 0 to 1, because it's around bounded by the horizontal line y equals 1. All right, so those are my limits. Now I've got pi, and then my radius. So radius on this one, we need to think here. Think about how we're going to come up with this green shaded region, right? Now again, it's not just going to be the function, because if we had just used the function value as our radius, then that would give us this area. That's not what we want. We want to somehow come up with that area. Well, we've definitely got 1 involved in here, and somewhere that's our top value, right? So if we're looking for the space between this one and this one, to find the space between that, well, we actually kind of just want to subtract out this much. We're going to take all of it, the area under 1, except we want to subtract out this yellow. Subtract out. So how we find that space between is we do sort of do the top minus the bottom, if you will. It's kind of like finding the area between two curves, our top function minus our bottom function. Top minus bottom. And that leaves us with the space between. So our top function is 1. So it's going to be 1 minus our function, square root of x squared, dx. So our radius is just 1 minus the square root of x. All right. So whereas kind of a general rule is still is kind of whatever's on top is your sort of just top minus bottom. In this case, the axis was on top and the function was on the bottom. So we did our top minus our bottom. So it was the axis minus the function. And if it was the opposite way around, if the function was on top and the axis was below it, it would be the function minus the axis. So still the same principles of area where the top minus the bottom hold. And again, if the axis is just x, right? If it had said around the x-axis, then we would just use essentially the function minus 0. Okay, so there's our setup, and let's go ahead and just type that in to y1 pi. You can also pull the pi out if you want to and just multiply it at the end, but I think it's easiest to just type it all in your calculator at the same time. 1 minus square root of x squared, graph it, second calc, number 7, integral there from 0 up to 1. And we get a very small, which should make sense because this is a very small amount, these decimals here. I got 0.5235, so 0.524. Boom. All right. Typed it in that time. All right, I'll just go ahead and set up one more. All right, so this one, same deal, region bounded by f of x equals 2x cubed, and the horizontal line y equals 1. Find the volume when it's revolved around that line y equals 1. Okay, so we're going to always want to identify what you're revolving it around first. In this case, it says we're revolving it around y equals 1. So this is our axis of, it's called our axis of revolution. Technical term, right? Axis of revolution. So this one gets rotated, and we sort of again get this shape here, right? That's where we're finding that area of that volume cut into these discs. All right, so we've got volume integral from 0 to, now it doesn't actually tell us what that point is. We need to figure out what that point is. We can do so pretty easily. It's just going to be where the function hits the line 1, basically, right? Where it hits the line y equals 1, because we want the x value, right? It doesn't go all the way to 1 in the x direction. So we need to know where that equals 1. So where does 2x cubed equal 1? And that's just going to be divided by 2. So x cubed equals 1/2, and then take the cube root. So it's the cube root of 1/2. It's probably best to just leave it like that for upper limit up there. the cube root of a half rather than worry about decimal points. Easiest way, just type it in like that. Okay, and then let's figure out what our radius is. We got pi. Another easy thing to forget is to write that pi. Our radius here, let me go ahead and erase some of this stuff. Our radius, again, is not just the function. It is sort of the top function minus the bottom function, right? So because we want the area between. So it's the top, which is the line y equals 1. So just 1 minus the bottom here, which is the function, 2x cubed, and that whole thing squared dx. So that's what we're going to type into our y equals. Again, you could do this by hand. I wouldn't advise doing it by hand, but you can. This could be just a multiple choice question on the AP test because it really doesn't take long to do with the calculator. Right, and graph, second calc. And we're going from 0 to, and again, I'm just going to type in the cube root. So I'm just going to math cube root of 1/2. And I got 1.6029, so 1.603. It is a good idea in this video to try typing some of these in. Make sure you're getting the same answers as well. 1.603. All right, that's all, folks. Here, again, if you want to look at that three-dimensional figure there that I kind of tried to draw, see it. So it's kind of neat, and you can see these disc cross sections here, right? That's a disc. All right, that's about it. If you are struggling with this, make sure you do reach out to me, and good luck, guys.